Hello. Okay, I'm going to go through the requirements for a chemical engineering Bachelor of Science. I graduated from UCSB, so I'm going to look through the requirements at UCSB for chemical engineering, but they're generally applicable across a lot of different schools. Um, so at a high level, what is chemical engineering? Chemical engineering is you want to go through this degree, you'll know how to basically take a raw material and then use chemistry, use process controls and use different sort of physical phenomena to transform that raw material into something useful for the world. And so I'll go through like the classes and how those classes let you understand that sort of world view and like what sort of how those classes let you gain the ability to do so. And I'll go through those requirements right here. Um, Okay. So for chemical engineering, you have to take there's an introductory chemical engineering class that we had to take freshman year. And then there's like another introductory chemical engineering class that we take our whole sophomore year. And then we take our gen chemistry, and then with that, we have general chemistry lab. And then we have OChem and OChem lab. So this is OChem lab and this is OChem. But we only have to take 2 quarters of each. And then like OChem sequence is 3 quarters. And then we have how to program, which is we learn MATLAB in this class. And then we have to take math up to differential equations, vector calculus, like basically 3D calculus and stuff like that. And then we have to take general physics 1, 2, 3, and then the third physics we have to take a lab with it. Okay, going into our upper division classes start our sophomore year. Also some of these classes go into our sophomore year too, but like these happen at the same time. So for example, Chemie 107, we do that winter quarter of sophomore year. That's a introduction to bioprocess engineering or something like that. Yeah, bioprocess engineering. And then we take thermodynamics. There's a technical communication class that we take with our lab classes. We have our sequence. We have separations. I'll go into detail on what all this stuff means. So we have a math sequence that we take. And we have a reactor engineering sequence. We have controls. We have chemical engineering lab we take. Chemical engineering design that we take senior year. That's when everything all comes together. We have to take physical chemistry. Some colleges, maybe you have the option of taking biochemistry or physical chemistry. Over here, we have to take physical chemistry. And only B and C because A is thermodynamics, and we already took thermodynamics our sophomore year. This is our junior year. And then we have an introduction to material science class that we take. And then with all that, we have to take 15 units of technical electives. So that means 5 extra classes from here, but also you can petition to have your technical elective from another department or something like that. And that will count too. So yeah, usually these classes are 3 units. So that means we have 5 extra classes of technical electives. We have these classes here. We have our preparation for our major here. And then being a UCSB student, we have to take our general education requirements here. Yep. And then you can take other classes for fun too. Yeah. Yeah, but yeah, if you do your player cards right, you can have space to do fun classes your junior and senior year by taking like maybe online classes over the summer, like GEs over the summer. GEs are your general education classes. And yeah, and then you have some of them back out here. And then you can, yeah. Okay, so here's how your curriculum would look like. So your freshman year, you're going to go through your chemistry, your general chemistry. What does that tell you? Your general chemistry is gonna introduce you to chemicals. Um, yeah, and then your chemical engineering 5, that's gonna introduce you to sort of the engineering framework that you're gonna have to think about through your degree. So yeah, chemistry you learn how to like balance reactions, you learn about the thermodynamics like at a very high level of why reactions go proceed one way or another way, or like acid base stuff, some introduction stuff to chemistry. Um, and then with that, you start your math classes, so you learn your calculus. So calculus is looking at graphs and and Why is that important? It's just, you learn how to play with equations when you learn a calculus. You learn how to relate variables together and stuff like that. Yeah. You take your physics classes. In physics, you learn your mechanics, your thermodynamics again, but from a physics lens. Just a lot more equations with your physics classes versus chemistry. It's just a lot more concepts and thinking about chemistry. Um, and then in MATLAB class, you learn how to code in MATLAB. Um, Linear algebra, you do systems of equations. You solve like you can put like five systems of equations in a matrix, and you can solve it through. That's what your linear algebra class tells you. And in your differential equations class, that tells you how to solve differential equations because oh, right, okay. So a lot of things like chemical reactions, things happen with a rate over time, right? Like your amount of chemicals in a chemical reaction change over time. And so if you want to maybe solve for your concentration, like a equation for how to track your concentration of that chemical over time, you're gonna have to solve a differential equation to do that because you relate your like number of chemicals over time equals the rate of reaction. And so you just have to solve uh that equation out and you get to get your when you solve that differential equation, you get an equation for concentration with respect to time. And so then you can predict like, hey, there's gonna be this many chemicals after maybe 10 seconds or something like that. And so that's why your differential equations class is important. That's why your foundation in calculus is important. And then when you scale it up to like vector calculus and 3D calculus, it's important because then you know your rate of volume with respect to time and how that changes and stuff like that. Like how much stuff is flowing through a certain area. Like if you have fl energy, right, flowing through a heater or something, and it's like flowing through a 2D surface, but it's flowing through in the direction that's normal, like at a right angle to that surface, right? Then you use your vector calculus knowledge to figure out, hey, this is how much energy is leaving that surface area of things. Yeah. Okay. So then, um, okay, cool, cool, cool. And then, so yeah, what is your chemical engineering 5? That's your introduction to chemical engineering. You just learn like, hey, this is how you can like something going into a chemical reactor or something. You're like, okay, there's potatoes going into chemical reactor, and there is oil going in well, also going in, and then you want to figure out how many potato chips can come out of that. So maybe like okay, each potato gives you five potato chips. So if there's 10 potatoes going in per minute, then you get 50 potato chips out. That's just a very basic example. I mean, obviously you do it with chemicals. Like, hey, there's there's water, and let's see. Sure, there's water and salt going into this mixer, and you want to figure out the concentration of salt water that comes out. And so you just like add the things together and then divide by the total volume, and you get your concentration and stuff. Something like that. So you go into that a lot deeper in your chemical engineering 10 class, which is your sophomore year version, and then you also learn about like, hey, these are the equations for energy, and then you know like, hey, this is how we can balance out energy through that unit. So like, hey, you need to input this much energy to drive the reaction forward, and the reaction outputs this much energy, and then you need to balance that out, and that's what chemical engineering 10 is going to tell you. Okay, cool. So yeah, your freshman year, fall quarter, you take your introduction to chemical engineering, your chemistry lab, your math class, and some writing class because it's a requirement for the university. So winter quarter, you take your no chemical engineering classes now. Chemistry lab, math, physics, and your writing requirement. Spring quarter, you take your chemistry lab, your math lab class, your math class, your physics 2 class. Okay, cool. Sophomore year, You're going to take your chemical engineering 10 class, and then you learned about that. And then now you take your first OChem class. You're going to take OChem A as long as alongside math and physics lab. Yeah. Um, and then if you're ahead in math, you just like push it up the quarters respectively. And then it opens up these quarters out here. And then, okay, so your OChem A class, what do you learn? You learn about organic chemistry is the chemistry of molecules with carbon, usually carbon and hydrogen. Um, so you learn how to classify different organic molecules in this class. You learn how they react with the environment, how you can look at it at different angles. So you learn about like the shape and structure and reactivity of these molecules, of these carbon atoms, because these carbon atoms are basically what make up a lot of life. And so learning organic chemistry basically tells you the chemistry that is involved with a lot of life and a lot of like plastics and stuff like that, like because plastics is made out of hydrocarbons and stuff. So yeah, there's that. And then you take your OChem class. You OChem class part two. That one's just going to tell you a bunch of different mechanisms by these organic chemicals react by. So your bioprocess class, that's Chemie 107 right here. Bioprocess engineering. You learn about okay, so yeah, in a bioprocess unit, right? So in a biochemical reactor or something like that, you can basically design, you can have bacteria in there that spit out different drugs and different chemicals of interest, right? So you can DNA makes proteins, and you can basically design a DNA, put it inside a bacteria, and have that bacteria spit out the protein that you want to manufacture. And proteins are useful because you can make proteins that are pretty stable. So maybe you can use a protein in a detergent, and that protein in that detergent latches onto dirt or scents and stuff really well and decomposes it down and then into like waste and stuff like that. And so, or you need to make a protein that's effective for targeting a certain disease marker or something like that. Yeah, anything, right? And so what this class teaches you is like, hey, this is like how bacteria grow in a reactor, how you would need to set up the reactor, how we need to model it with the equations and stuff and stuff like that. And then it also tells you about the nitty-gritty of like molecular biology and how you can design DNA and what the process is and from DNA to protein is and all that stuff. Okay. And then you take your chemical engineering thermodynamics. This is more of your like chemical engineering. Like this is the one that overlaps pretty heavily with mechanical engineering. You learn about like thermodynamic cycles and stuff like that, like heat engines and stuff like that. Basically like how your car runs, how you're gonna learn the cycle for the piston, how like you can heat up gas inside a piston, have it expand, and then force and then have some sort of reaction or a combustion happen and then it falls down and that moves the motor and something like that. Yeah, that's that. And then you take your OChem lab. This OChem lab corresponds with your OChem part one. So in your OChem lab, you just like go through the reactions that you learned in organic chemistry and have the lab component to that. You basically, so chemistry gives you intuition of how chemicals work, stuff like that. And then you vector calculus is Math 6A. Okay, spring quarter sophomore year, you take your chemical thermodynamics part two. This one's more specific thermodynamics to chemical engineering. So you learn about like how solutions, the thermodynamics of how different solutions mix together. So you can, when you mix together solutions of different densities, for example, and how they might partition between each other, like oil and water, for example, you can learn about, hey, this is the chemical potential of a oil molecule wanting to go into water, and that's why its phase separates out. Or when you have solutions like alcohol and water of like two different vapor points, you can mix them together, and you know why that solution's boiling point is different than what they are separately, and also why they're when you mix them together, how the why the volume might change and stuff like that. And so you learn that, and And yeah, yeah. And you learn about like all the different variables like entropy, temperature, other stuff. And there's differential forms for that. So like when you have a system that's always changing, you're gonna have a differential form of like for entropy and stuff like that. And so for that, you're gonna have to understand how that works and stuff. Okay, let's look it up now because now things are getting a little bit more complicated. So it's gonna be important that we understand what's going on. So okay, what is chemical en engineering? Um, okay, let's see. So, what are some concepts of fugacity? Let's see what fugacity is all about. Uh, okay, let's just go here. Okay. Yeah, so this is like the differential form equation. So this is your chemical, the differential form of chemical engineering. Chemical potential is equal to this. That's your entropy, the temperature. Yeah, so these are variables how you can relate things together. And so like your ideal gas thing is like that. But then when you have your fugacity thing, you're gonna have to have another version of the differential form. You need to differentiate it out. And so that's why you get that little difference. And yeah, so you're basically you're gonna learn a lot of different ways to move from an ideal gas or ideal fluid way of thinking to a real gas or a real fluid way of thinking, so that you can make relations to the world around you more realistic. Because everything isn't ideal. There's gonna be interactions that you have to account for with all these different things, and so that's why you have to take that into account with stuff like this. Um, and then it's just a bunch of equations, honestly. You don't really go into like where this stuff comes from, unfortunately, I will say. Just to like accept like, hey, this is a relation that relates to real gas and stuff. And yeah, and then you just use that to try to solve problems for real systems in the real world. Yeah, and then okay, so now we begin your math sequence, your spring quarter of your sophomore year. So this is your analytical methods class. This is where you're gonna solve differential equations for the exact solution. So yeah, imagine an equation that needs to be in like three variables, and you know solve that differential equation with like space and time. So you basically learn the methods to break down that equation and solve it through. And that's important because you need to use those techniques to solve a lot of the equations for your transport classes. Okay, cool. So yeah, then we do your transport classes, your Chemie 120 ABC. So your 120A, that's mass transport. So here, let's go into Navier-Stokes. This is where you're going to learn the famous Navier-Stokes equation. Yeah, so you would like see this thing. It has like a bunch of variables and you solve it through. But the good thing about this is that you can make a lot of assumptions. So maybe you only have to worry about it in like your y momentum. Maybe you only have to worry about it in the directions that's not y. So then you have your time, your x, and z. And then maybe also it's at steady state, which means that it doesn't change with time. So you cross this out, you cross out this one, and so you said dx dy equals this thing. But also another good thing is in your analytical, so in our, at least in our analytical methods class, we learned how to use Mathematica. And with Mathematica, you just basically put this differential equation into that software and it solves it through for you. And it also, yeah, it solves it through for you. So what is this Navier-Stokes equation anyways? Um, okay. So yeah, what is this? So it's basically showing you how volume changes with time with respect to like pressure, gravity, and diffusion, I guess. Um, um, but like, what is this? What? Okay, let's see. It's basically. like how basically is able to model how fluids flow and the like the 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 flow rate and the behavior of the fluid as it flows through pipes and stuff at different pressures and stuff like that. That's important to know because then you can model how the fluid would flow through a chemical process at unique, like very extreme conditions that you might not understand realistically. That might not be like intuitive. Yeah. So yeah, it describes like you can track like the different flow patterns of how fluid flows and stuff like that. It's important because with these flow patterns, it can disrupt the behavior as it moves through a process, and that can basically disrupt the piping and stuff that is involved with that. Yeah, okay, so then your 120B, that's your heat transfer class. So then, let's see, in your heat transfer class, you're going to learn how heat gets dissipated, um, like with different fins and stuff. So 2D fin heat transfer. So something like this. And this is important because heat can build up pretty easily in a process with chemical reactors and stuff like that. So if you want to like design something like this that is able to like transfer heat at the rate that you need it to, then you need to understand the equations involved with heat transfer to do so. So like what are the equations then? Yeah, it's similar to like fluid flow, but there's like an analogous like equations in heat transfer, and you just make a bunch of assumptions and you solve these equations through. Again, you see these differential terms like temperature with respect to space. So, like at different parts of X, right? Your X is flowing outwards. Your temperature maybe drops down, so maybe your temperature is your highest here and it drops down there. You basically want to know your temperature profile with X, so you know how long you need to make your rod and stuff like that. Yeah. So you just use these equations, solve it through. Yeah. Okay. And then your mass transfer class. Let's see. So mass transfer is like how physical molecules would flow from point A to point B, like through diffusion, which is like just on its own, or maybe through other forces that might do it. So like convection. Let's see, convection. Yeah, so like you might have in a process water might be flowing through down, and stuff like your chemical product might be stuck to the sides of the wall, right? And so you want to know what your mass transfer is of your product going into the water so you can collect it at the bottom. And so you can use like your convective mass transfer terms to solve it through. So let's see. You use diffusion and convective mass transfer to understand that relationship. So yeah, stuff like that. Yeah, like use these equations. I think these are differential equations I have to solve for. But again, equations, you know how to solve equations at this point. You basically, at this point, is just learning how different equations relate to different scenarios, and you go through solving it a few times, and you basically know how you can apply that in the future when you need to. Yeah. Okay, cool. So that's your transfer classes. Okay, and in your separations class. So in your separations class, so a lot of the core of traditional chemical engineering lies in like distillation columns. So here is a distillation column. So what is a distillation column? Like for example, oil, oil can go into a distillation column, and basically your heavy heavy parts of the oil is made up of like a bunch of different hydrocarbons. The heavier hydrocarbons would fall to the bottom, whereas the lighter ones will go to the top. And that's because the lighter ones want to vaporize more quickly or have a lower boiling point. And so because of that, because of their lower boiling point. That's why it's cooler at the top, and then it's hottest at the bottom. Um, and so at the bottom you get out uh, your heavy oil elements, and then at the top you get your light oil components and stuff like that. So like right here, and then you want to figure out, hey, I need to separate out in between, in between this distillation column. You basically the point of distillation column is to separate out the components at certain purities, and that's the whole point of like the separation class is to model with equations how you can get like a 99% purity up here and maybe like a 98% purity up here and stuff like that. And so yeah, so let's see. I see. So then you need to, like, there's equations that go along with the different phase transfers that happen in between the trays, and you can basically model like if there's things that you can use. There's like phase diagrams that you can step between to figure out the different purities of like that get involved with the different number of like trays that are involved with that. So yeah. Yeah, like you basically have to balance everything out. Like you have to figure out like, hey, this much mass is going up, this much mass is going down, and then all that stuff, use those variables to just use the equations to figure it out. Um, yeah, but I mean, you would learn how to distillation column works and how to separate out components at different periods, basically. It's not just distillation columns. You can have other things, other units like RO, stuff like that. Not just RO. Reverse osmosis. Yeah, so membrane and stuff. Yeah, you learn how to model that. Yep. Okay, cool. Okay, your 132B class is your numerical methods class. So instead of using analytical methods to solve out differential equations exactly, you can break up your differential equations with little time intervals, and you can use that sort of concept. So instead of having an exact solution, you have approximate solutions based on how you broke up your time intervals. So, like dx dt, that's just like x1 plus a little x2 in the forward direction. And so t1 plus t2, like a little t2 in the forward direction. And now it becomes like an algebraic equation that you basically solve for. So it becomes like an iterative equation too. So like it depends on the variable before. And this time, instead of like solving through it analytically, you can use numerical methods to solve it through. And you basically solve it through algebraically once, use that use the answer to solve for the next step forward, and then you basically get that so you get approximate points on that curve on like what that final form of the equation would be, and then you can basically approximate what the final equation looks like, not with an equation, but with time steps. Yeah, and also another cool thing is like you can yeah, let's see the golden search. I thought this was pretty cool. Golden search method. You learn how to like numerically solve for different maxima or minima. And how does this work? Da, da. Let's go to images. Yeah. Okay, this is this one. Um, basically, yeah, maybe you wanna. Okay, you need to. You basically break out like the curve into different intervals, and then you basically use the golden ratio or something like that, and you keep on breaking out the thing into the golden ratio until you narrow in to the until you narrow in into the minimum or the maxima. And yeah, you're uh okay, but kind of forgot what the how the golden search thing works. But Um, okay, here for example, here. Another, you can use like midpoint or something like that. So you know there's gonna be one minimum between this section right here, right? So then you you're in this total space here, and then you find the midpoint. From 0 to 10 you have 5. And then okay, you look at 5. Is 5 less than, so 5, is that one less than here? And if it's less than here, okay, so this one is less than this one. 5 is also less than this one and this one. So you know that 5 can be a solution. And then okay, so now you're in the middle. Now you have to go between 5 and 0. So 2.5. Okay, it's 2.5. What is that? 2.5 is both less than this one and this one. Um, so then now you know that has to be in between 2.5 and 5 because 5 is less than 0. Um, and then now you look at the midpoint of 2.5 and 5, and you know that that midpoint is larger than both. Wait, and then you know that that midpoint is larger, less than the 5, but larger than its 2.5. So then you have to keep your 2.5, and then so you keep your 2.5, and you look between 2.5 and 5. Midpoint between 2.5 and 5 is whatever that is. And then so you keep your 2.5, and then your new end interval becomes that. And basically it shrinks until it narrows into basically I think like the midpoint is sorry, the minimum is around 2.5. So yeah, it shrinks into that area. It converges onto that thing. Okay, anyways, that's your numerical methods. And then your winter quarter of your junior year, you that's when you start taking PChem. So why do you start taking PChem B and C? Because PChem A, that's thermodynamics, and you already took thermodynamics with chemical engineering 110 A and B. Okay, so then your PChem B, sorry, what Chemie 132C, that's your statistical methods class. You learn about like machine learning methods, you learn about how you can visualize data with dimension reduction, how you can use statistics to predict if something is significantly different than the data set, or like if two data sets are similar to each other, or if they're significantly different, stuff like that. You learn all the your stats stuff in your 132C class, and that's important because you know like how to statistically analyze data points when you're doing experiments and stuff like that. And experiments are important to model how different things might behave at the plant level. And while you're scaling up, like, hey, this is your chemical reaction, you have points tracking for the chemical reaction, showing like this much conversion here. But then you change this, is that you change the temperature, is the temperature gonna give you points that are significantly different than what there was before and stuff like that. Or maybe you change the whatever the material. And if it is going to be different, then you can investigate like what happened there with the physical phenomena. Yeah. Okay. So PChem, yeah, that's your quantum mechanics class. So that's going to tell you. Okay, what's that going to tell you? Let's go here. Like a particle in the box. What is that? Box equation. What is this? So it tells you a particle can only reside inside the box. This is your potential energy. Potential energy equals 0. So this is potential energy equals infinity here. And because of that, you have your bounds. Um, and yeah, you basically know in that box your electron can have these energy levels based on the wave equation and stuff like that. So yeah, you solve this equation for some reason, and you learn where your particle in a box stuff is, and you can basically predict like your energy for different electrons at different energy levels and stuff like that. Um, just gives you more physical intuition of how chemicals work. Okay. And then your spring quarter. It's a pretty heavy quarter. You take your technical writing class that goes along with your chemical engineering lab. So your chemical engineering lab is that's Chem 180A, and then you take your mass transfer. We went over what that means, and then that's when you start your chemical chemical reaction engineering class. That's 140A. And then your PChem C. Oh, and then sorry, you take your introduction to material science your winter quarter of yours junior year also. So what is that? So you learn about like different crystal structures of materials. So yeah, so like this, you learn how to calculate how the chemicals might arrange, or sorry, how the atoms might arrange themselves. You learn about m- metal phase diagrams. Yeah, you basically look at this thing, you look at like your temperature and your temperature and your alloy type, so like how these two chemicals things are and stuff like that. And stuff like and you understand how this stuff works now, I guess, with this thing. Um like what temperature it might exist at and stuff like that. Yeah, that's your material science class. You take it with we took it with mechanical engineers. Um, yeah. Um, and then 120C, mass transfer reaction engineering lab. So in your lab class, you're gonna basically go through the concepts you learned so far. So like how fluid flows. Maybe you have like a heat transfer experiment that you do. You have a distillation column, like we use like a batch distillation column that we had at the bottom. We had a batch of solution, and we just had trays in the middle, and we had to model how things would separate out, and we actually measured it and saw if our model predicted what actually happened, and we analyzed what went wrong if it didn't happen that way, and so stuff like that. Um, 113C, chemistry 113C, that's your statistical mechanics class. So this time you're using statistics to uh, mod like predict the energy levels of electrons and stuff like that, and how the distribution of electrons might fall over a lot of electrons and stuff like that. Uh, More intuition on how reactions and chemistry and molecules existence. Um, Okay, and then your chemical reaction engineering class, your 140A. What is that? So your 140A, this is when you're gonna have in the actual unit that converts your reactants into products. So you get a model that there's multiple different reactors that might exist. So there's a CSTR, continuous stirred tank reactor. And so in your continuous stirred tank reactor, you have your flow rate, right? So your flow rate, that's gonna tell you like your volume, change of volume over time. That's how that's related. If yeah, if Q out equals Q in and stuff like that. So in this, it's basically a tank has got a low stir, and in that stir you have your concentration going in, your concentration going out, and in that it's supposed to have a reaction going on, and you can model how that reaction goes on, stuff like that. And then when you have like multiple CSTRs together, let's see, what is the equation for CSTR? So here's what CSTR is like. Okay, so your volume times concentration over time. What is that? Volume times concentration over time. So the volume of reactor, concentration is your number of moles of your like your A reactant A over volume. So basically it's just the number of moles of A over time. So how is that changing? Your moles of A over time. So your reaction of A converts to B in here. What's happening here is A is going to B. So what's happening? So your in minus out plus accumulation is what's happening here. So that's your basically chemical engineering is in minus out plus accumulation. Sorry, in minus out plus generation equals accumulation. So this is your accumulation term. Yeah, this is like how much moles are accumulating over time is basically what this is telling you. And then that's equal to what's going in. How many moles are accumulating equals what's going in. So that's your flow rate, FO, of your initial flow rate times your concentration of A. And that's basically how much of A is in that flow rate. Because your flow rate, right, this is moles over time. And this one is going to be, your flow rate is going to be volume over time. And then this is going to be moles over volume. So your volumes cancel out. And then it becomes moles over time. So make sure your units work out. So like on one side of the equation, units have to be equal to the units on the other side of the equation. Okay, cool. So then you know, and then you have your flow rate going out. So you basically like draw a boundary on the entire thing. You know what's going in, you know what's going out. So then what's going out is gonna have a minus sign to it. And your minus sign, that's your flow rate going out. And then multiply that by your concentration of A going out. So now you know basically from here to here, you know that this is your difference in your concentration of A going out. Like this is what the difference of concentration of A is in the system. And then what's happening in here? Inside this tank, there's a reaction going on. So if your volume times your reaction constant, your A converting to B, and it's being consumed. Your A is being converted to B. So that's why there's a negative sign there. And then that reaction constant gets multiplied by your concentration of A. And basically, these units work out so because the units of the reaction constant are such that it becomes moles over time. So basically, what's going on is your moles of A going in, your moles of A going out, and then minus how much of the reaction A is being converted to B, and that's going to be equal to the moles that accumulate over time in this reactor. And so basically, um, the moles would decrease overall because it's being consumed by the reaction. Yeah. So, accumulation doesn't necessarily mean like, hey, it's being generated. It's being added to the system. It could also mean it's being depleted by the system. Anyhow, so now we go to B. And so same thing here, your B going in. So B is like your product this time. So A going to B. But hey, so maybe this reactor has a recycle stream, right? So what does a recycle mean? Recycle is like just like the stream going back into the thing again. Um, uh, yeah, maybe there's no good diagram for that. Anyways, uh, yeah, anyways, okay. So then you have your accumulation of moles of B over time is equal to in minus out, and then plus your generation term. Same rate constant. It applies to both equations because the amount of A being consumed is equal to the amount of B being generated. So this time it becomes just a positive sign. So VKCA. Um, and it's just basically these terms are the same because this reaction is only dependent on Ca. Um, yeah, because the amount of A being consumed by the reaction is the same amount of moles of B being generated by the reaction. So that's why these two terms are just the same. It's just one is minus, one's a plus. And so basically that's the CSTR. It's basically in minus out plus the reaction. And so now what is a bunch of CSTRs together gives you a plug flow reactor. So how is EFR related to a CST? So, CSTR basically has a reaction going along it over time. And a CSTR is just basically a bunch of, sorry, a plug flow reactor is basically a bunch of CSTRs together, I think in series or something like that. So, like, you have another equation to model the plug flow reactor. Um, so yeah, your concentration over time, and then you basically have these equations out. You solve it through. You learn like where these equations come from in the class, but yeah, know that like that's how this stuff works. Let's see. Yeah. So, stuff like that. And then, so then you go through that. You know your mass transfer, you know all your transfer classes now. You know how to design reactors. You apply that in a like chemical engineering lab class. You know how chemistry works at this point because you take PChem, OChem, and GenChem. Um, yeah, stuff like that. And then now you're in your senior year. Senior year, these are your basically last core like concept classes for chemical engineering. Your 140B, that's your reactor engineering part two. So in this one, you learn about like catalyst sites and stuff like that. So like the Admir isotope model. So let's see what this is. A fundamental physical chemistry equation that describes the monolayer absorption of molecules onto a solid surface. So how your catalyst like allows for reactants to adsorb onto a surface. So and basically you learn how that works on like your surface sites, your catalyst sites, and stuff like that. You basically figure out where these equations come from. Basically, you map out all your surface sites. You make a balance of like, hey, this is your term that would like that's your reaction rate that would adsorb onto the surface, and you basically solve it through to figure out that. And then you can also combine it with like mass transfer. So how reactants flow into a molecule that has a bunch of catalyst sites inside it, and you have your mass transfer term, and then you have your reactor engineering, like your mass transfer term, and then you have your reaction term for how it absorbs onto the site, and you can also have your like chemical reaction, your actual term. And so basically, you learn how that gets all modeled, and the time it takes for doing all that stuff. Yeah. And then and then you go into your winter quarter, you have your final chemical engineering lab here. You basically pull everything together. You do a more complicated distillation column design. You do a more complicated reaction and engineering design class experiments. You do some like momentum, your fluid flow experiments and stuff like that, like diffusion and mass transfer experiments and stuff like that. That's what you do in your chemical engineering part two lab. That's 180B. And then you start your design sequence. And so in your design sequence, that's when you learn how chemical plant design. And so that's when you start designing your chemical plant with a bunch of different processes. So in that. Um, let's do a flow diagram. And then you also like model the economics and like all your other real life situations that you need to deal with real life situations and so for like with companies and stuff. So flow diagram. Yeah, okay, cool. So in this class you would basically like design something like this if the quality gets better. Maybe this one's easier to see. If the quality, okay, cool. I mean, it's gonna be a lot more complicated than this, but basically, you have a simulation software, and then within the simulation software, you know what sort of equations are going on, what sort of relations might be inputted into the simulation to get you the prediction. So you would basically make a MATLAB code to predict this stuff on your own. You can use a simulation to also help you predict this stuff, and your goal is to basically we're going to give you a reaction, a reactant, a reaction, and some guidelines and stuff. And you need to figure out how to turn that reactant with that reaction into the product at the purity that they're requiring it to be, and then at the economics that they're requiring it to be. So stuff like that. And then how much? Yeah, stuff like that. And so that's when you like use this stuff, you model it they're going to give you economic relations that you can use, and then you basically feed in you basically understand like, hey, the reactor design is going to follow this equation. This is what I can predict it to be. This is what I'm going to put into the simulation, see if it's a realistic prediction. And what's wrong if it isn't? I'm just going to keep on playing with it until it does become something that I want. And then the reactor is going to output my reactants at this concentration, and it's all going to be jumbled up into a bunch of so it's all the chemicals are going to be jumbled up, and I need to separate out these chemicals. And so then you're going to have like separation units, you're going to have the distillation columns and stuff like that. And you're going to want to supply energy to all these different units, but then how do you integrate all the heat together? And so you're going to have heat exchangers. They're going to be like, okay, so this reaction is going to give me this much heat that I can use to supply the heat to this distillation column. So I'm going to use a heat exchanger to get my flows into those units to be the temperatures that I need it to be so that they react in the concentrations that I want. And so you use all that, you build out all those units, you learn the trade-offs like, hey, if I added heat exchanger here, it's going to cost me this much, but I think it's worth it because it's going to save me this much in energy and that the energy costs this much and stuff like that. So you think through all those design choices and you basically pull together, you design your entire plant and your flow rates and energy and consumptions and stuff like that through everything, and you present that to your class, and that's your design project. And so um, at this point, you're pulling together a lot of the stuff that you learned in your previous classes. So like your general intuition on how chemistry works, your physics knowledge that you built throughout your general physics sequence, but also all throughout your chemical engineering classes. And then like how you model the physical phenomena in those classes and how those equations, how you can think about those things in with different equations and stuff and just basically developing that intuition and you apply that sort of thinking towards trying things out in your design class and you basically try your best to design the most economically feasible and efficient plant that you can for that class. And so yeah, that's your class. That's your chemical engineering curriculum. You're gonna learn a lot of chemistry, you're gonna use a lot of math, um, and you're gonna you're gonna do all that. And at the end of the day, you learn a pretty good amount of stuff in this class, I would say, in these classes. Yeah. Right.